Dear all, thank you very much for joining today's Space Syntax Lab seminar. I'm delighted to welcome Chenyang Li, who will be presenting part of his doctoral research, which he has submitted a couple of weeks ago. Today, he will share his methodological developments on evaluating graph structure under the title, The Need for a New Measure of Quantitative Spatial Description. Chenyang is an EPRSSC-funded PhD candidate here at the Space Syntax Lab, UCL. His research focuses on the spatial types and structures of complex public buildings, with a particular emphasis on museum and art galleries. He is also a postgraduate teaching assistant for the MSc MRes Space Syntax Architecture and Cities program and the MPhil PhD Architectural Space and Computation program. Before joining the Bartlett, Chenyang worked as an architect at the Hunan Architectural Design Institute and served as a guest lecturer at Hunan University and Changsha University of Science and Technology, where he contributed to space syntax workshops. Before we begin, if you have any questions during the talk, please put them in the chat so we can address them at the very end during our Q&A. And now please join me in welcome Chenyang. The floor is yours.
Thank you, Kimon. I'm Chenyang Li. I have actually just submitted my PhD thesis at Bartlett. I'm supervised by Professor Sofia Sara and Professor Sean Hanna. And today's presentation is one part of my PhD work about some methodological developments I've made for the quantitative description of the complex building layout. Basically, this work is based on the very last paper Bill Hillier presented in 2019 as the keynote for the Beijing Space Syntax Symposium. In his final work, Hillier identified this theoretical challenge of the current space syntax theory to make it more, in a way, scientific and retestable. So in response, he proposed this idea of the graph structure as the fundamental concept for advancing this theory. To start with, Hillier uses Tate Britton as a case study to explain what is structure. So he refers to an earlier study in, I think, 1996. So he and other colleagues discussed the notion of the churning effect, which was observed in the Tate Britton at the time, and that is raised by the frequent re-encounters during the visitor's journey through the gallery. And in this very last 2019 paper, Hillier revisited this notion of churning effect and argued that such phenomenon is fundamentally predetermined by the structure of the spatial layout itself. So he discusses from a very simple experiment. If you look from this figure, so suppose there are 100 people entering the gallery from the entrance, that the room A at the bottom. If in every space the visitors split evenly when there are more than one directions, so by chance, with a large number of route alternatives, there will always be a certain number of people that eventually re-encounter with another group of people with a very different route choice. Say, this is a kind of a calculation. So 1.23 people will go to room 14 following one route. And another group of people, 2.78 by chance, will also go to room 14 and meet this other group by a very different route. So what he actually argued here is that the potential for such re-encounter that cause the churning effect is structural, that is prior to any other factors, but simply a calculatable chance. So building on this kind of structural perspective, Hillier identified two challenges for this development of a methodological framework to categorize and compare such spatial structures. So there's a theoretical challenge about how to classify the properties of the spatial structures so that different forms can be meaningfully distinguished from one another. And there's a numerical challenge about how to identify the variables that can actually predict specific functional outcome, such as churning, out of the spatial structure. So, starting from the notion of the theoretical challenge, Hillier in the late 2019 paper critiqued the limitations of the existing classification of A, B, C, and D type of spaces, which I assume most of the audience may be familiar with. Particularly, he noted that some space types are defined relationally, like the definition of a B space it really depends on the existence of an A space, right? Since it's defined as the access route to a dead end. So to address this limitation, Hillier proposed that the four space types can be understood actually as the complete and planar graphs composed of 1 to 4 nodes. So A space corresponds to one node complete and planar graph. B space refers to the 2 node, then D space refers to the 4 nodes. And what is interesting that these 1 to 4 nodes of planar and complete graph are the only 4 possible components one can ever actually build, because theoretically there's no graph that with beyond 4 nodes that can remain both complete and planar in the two-dimensional world. So I quote Hillier's explanation about the complete and planar graph. Basically, complete graph is one which every node has a direct link to all the other nodes, and the planar graph is with no link cross each other, right? So Hillier, building on this perspective, further argued that, okay, so now we have the redefined classifications of the 4 space types, then we can actually see these 4 space types as 4 fundamental syntactic mechanisms for generating the spatial configurations, which leads to the idea of 4 type of structures. So basically, so say if we put the A structure as an example, so A structure here is one node and it's a dead end. So if we want to add more A space, following the logic of A space to create this configuration, we are adding more and more A space dead ends to the existing graph, right? So Hillier used the naming system like A structure is the star, B structure is a path, C structure is a cycle, and D structure is a wheel, as from the notion of deformed wheel. And each structure type and their associated functional effects can then provide an effective means of evaluating the impact of the spatial layout on the social functioning. Uh, yeah. And in response to the other challenge, Hillier proposed the measures of traversability and mean local choice. This is actually very two original kind of concept by Hillier that is based on the notion of Hamiltonicity in the graph theory. Uh, this is very different from the existing depth measure that is widely used in the space syntax study. So I put here to make it clear for the calculation process for both the depth and the traversability. So we all know that the depth is calculated based on the single origin to destination calculation of the topological steps. So basically, if I want to calculate the depth of A space to others, I calculate A to B, A to C, A to D, A to E separately, then I sum it together, right? So 1 plus 1 plus 2 plus 2. But if I want to calculate this kind of, by this notion of traceability, so starting from node A, I find the very shortest path. I start from A to traverse through all other nodes, right, in the consistent visit. So with the minimum possible revisits. So for A, there will be either A to B to D to B to C to E, or A to C to E, back to node C, then B, D, right? There's always, you see, there's always one unavoidable revisit if I want to have a continuous visit starting from A to all the other nodes. So accordingly, so this is the measure of the traversability, and the mean local choice is quite associated with the traversability calculation. It quantifies the richness of the route selections for such shortest and efficient traversal. So although it sounds very similar to the original definition of choice, right? It's all called choice, but it's actually two very different concepts. So the existing choice, or the between centrality, if you may say, is in a way associated with the measure of depth. right? And the mean local choice is associated with the traversability for the continuous visit. I will have a further discussion on this in the later slides. And so in Hillier's paper, he calculated these three properties for the theoretical A, B, C, and D structure using the example graphs with 7 nodes. So with 7 nodes, we have these 4 kind of structured graphs, and then he calculates as an example of the 3 properties. And it is observed that, of course, different structure types have variations in the 3 properties. Like D structure is low in total depth, meaning it's more integrated, and also high in traversability and high in mean local choice. In a very extreme contrast, the B structure, the path, is segregated, lowly traversable, and low in mean local choice. And consequently, if I quote Hillier's word, each structure then has meaning, not in the sense of natural language, but in the syntactic sense of specializing concept and so reinforcing their expressing. So in other words, Hillier suggests that the variations in these structural properties are reflective of unique semantic implications of each structure type. And he used this concept of long and short model activity as the kind of social implications of the structural differences. So essentially, it's a very kind of existing idea, like long model activity indicates the restricted movement patterns under global constraints because the length of the restrictions is long. So we call it long model in a way. And it is correlated with A and B structure types. And on the other hand, C and D structure, argued by Hillier, are related to the short model activity. So he said C structure access and D structure creates the short model, leading to this kind of potential for a better free exploration, in a sense. However, my study kind of identified 2 key limitations in Hillier's 2019 study. The first is the absence of the quantitative evaluations in the theoretical models of the 4 structure types, because Hillier only provided examples of the 7-node graphs. So it actually kind of unclear whether the observed trend, whether it's high-low or low-high, this kind of trend, still exist when you have a graph with higher or lower number of nodes. And secondly, there's a lack of algorithm to calculate the traversability and mean local choice because they are all new measures of the real-world spatial configurations. Because in most of the time, real-world configurations are in between of different theoretical structure types, right? Hillier talked about traversability of tape written in his study, but he was only using the manual calculations in a rather simplified way. So it's hard to actually identify the accuracy and impossible to actually apply this approach of traceability calculation for more general use for the spatial analysis. So what I did in my studies, I tried to evaluate all 3 properties of the theoretical structure types towards any number of nodes. So say if we start from the calculation of depth, which is very well known, and if we look at this theoretical A structure with n number of nodes, right? So for the central node of this A structure, it requires n minus 1 steps to reach out to all the other edge nodes, because for each edge node is 1 step away. So the total depth for the central node will be n minus 1 because there are n minus 1 edge nodes. And for each edge node is 1 step away from central nodes and 2 steps away from the edge nodes. So for each edge nodes, the sum of the depths will be 1 plus 2 times n minus 2. And if we sum all together, so the equation to calculate the total depth for the theoretical A structure will be 2 times n minus 1 times n minus 1. And if we apply these similar calculations to all the other structural types following the syntax or mechanisms of creating such configurations, we can then have these all kind of equations to calculate the depth value of the theoretical A, B, C, and D structures with any number of nodes. Then we can then have observe these kind of curves regarding the value with different node count. And it's clear that A and D structure have very similar and also very low total depth values. So it means that A and D structure are comparatively more integrated. Whereas the B structure, the curve in green, has the highest total depth value, the path, right? And so this is a very common and understandable measure of depth. Then if we move forward to the traversability, which is Hillier borrowed from idea of Hamiltonicity. He said here, traversability will be maximal when no visits are required and minimal when there are a large number. And if we also calculate based on this logic, so essentially is to calculate the real number of steps required for each space in the configuration to traverse through all others, including the necessary revisits. So we have this kind of sum of the figures. Then we compare that with the theoretical minimum number of steps required with the same node count. So the highest value of traversability will be 1, such as the C and D structure, because there's no revisits needed for the traverse. And the traversability for the A structure eventually approaches to 0.5 when there are a high number of nodes. Actually, 0.5 is a theoretical minimum value if you imagine, meaning that for each step you take towards a new node, you need a step back before you proceed to the next node, right? So it's 0.5 because it's 2 times the theoretical minimum. If we divide the theoretical minimum by the actual steps, right? So it will be 2 times, so it will be 0.5. And the B structure traversability trends towards 0.8 if the node increases. And according to Hillier's definition, the B structure have low traversability. So we can then say, okay, so any value as seen from this evaluation at or below 0.8 in Hillier's logic can be defined as the low traversability. And lastly, the mean local choice. This is a brand new idea. This is not Hamiltonicity. This is purely Hillier's idea. He also proposed how to calculate that via the 7 nodes examples. So, I mean, from Hillier's argument, D structure, as we can see here, is apparently have the highest value of the mean local choice, whereas the A structure have relatively high as well. C and B structure both have very low, meaning that you don't have rich alternative options if you want to traverse within the configuration via the shortest path. But however, I mean, my study also recognized that there are inconsistencies in Hillier's example of calculation. So basically, Hillier used one logic to calculate the values of the A, B, and C structure examples, and another logic to calculate the D structure, which I will explain in the later slide here. So for instance, this is how Hillier calculates the mean local choice for the 7 nodes A structure. So basically, it is to sum up the choices provided at each step you have to traverse along the shortest path. So say if we start from the central node, initially we have 6 very same alternatives, right? Because all the edge nodes are the same. After we choose one and reach to the edge nodes, we only have one option, which is go back to the central node. Then if we want to take the third step, we cannot go back to the same edge nodes as we just visited. Otherwise, it won't be the shortest path. So we are left with 5 alternatives. Then if we reach the edge node and go back, then we have 4 alternatives. And if you sum it all together, it will be 6 plus 1 plus 5 plus 1 plus 4 plus 1 and blah, blah, blah. And then we have 26 alternatives along this route. And then the route length of this traverse is 11 steps. So if we divide 26, which are the alternatives, by the length of the route, which is 11, we have 2.36, which will be the definition of the mean local choice Hillier calculated for the A structure. And he also uses same logic to calculate B and C structure. Because if you look back at the B and C, we see the mean local choice is basically very approach to 1, meaning that once you make the initial decision of the direction, you don't have actually any options but to follow to reach one end for the B and then pass to the other end, or for the C is that once you make a selection of choice, you need to continuously go through the very end of the other side of the circulation. Otherwise, it won't be the shortest and simplest traverse route. However, when Hillier calculates the value for the D structure, he used a different logic. So as we can see, if we still calculate from the central point, and we have 6 alternatives, same as the A, but when we reach to the edge, if we follow the logic of this A structure, right, at the edge, we should only have 2 options to go to the surrounding edge nodes. We can't actually go back to the central nodes because otherwise you will have repeated visit, which makes it not a fully Hamiltonian route. But Hillier just simply adds all these kind of alternatives along this route, which makes 6 plus 3 plus 3 plus 3. And then he calculates that the mean local choice of the D structure is 3.5, a really, really high value compared with B and C. But if we actually use the logic he used for the A, B, and C structure, things are different. Like I said, if we reach out to the edge nodes, like from A to B, we only have 2 options to have the most shortest traverse, right? And then once we make an option from here, let's say we move from B to C, we then left with only one option because we can't go back to A, we can't go back to B, we can only move forward to finish the traverse, the most efficient traverse. So the actual alternatives, if we calculate from the logic of A structure, will be 6 plus 2 plus 1 plus 1 plus 1. And then the resulting mean local choice value for this node is 2. I mean, it is still higher than the B and C structure, but it's not that significant, as Hillier argued in the experiment. So building on this, the study here provides 2 evaluations similar to what it had done for the depth and traversability. So basically, it used both logics of Hillier, one for the A, B, and C, and one for the D structure, to make it consistent with all the structure types. And in addition, the study proposed an alternative way that is different from what Hillier did to calculate the mean local choice that we think that may even better represent what Hillier actually means about the measure of mean local choice. So regarding his intended contribution to the quantitative spatial description methodology, right? So firstly, we test the equations of the logic of Hillier used for the A, B, and C structure, which is the sum of choices across the steps needed to traverse from one space to all others via the shortest path. And the result is like that. So you can see the trends, the blue lines are for the A structure, red lines are for the D structure, and yeah. So we can see that D structure, if following this logic, have a consistent value of 2, as we have calculated in the previous slide. While the B and C structure approach to 1 when the node number increases. In a way, I think this result seems to violate what Hillier originally intended behind proposing the mean local choice, because it didn't really differentiate D structure from the B and C structure. Because, I mean, with the nature of multiple subcycles, one should think that, okay, so D structure theoretically should offer more local choices than the path or the single circulation. But here, if we follow this logic, it doesn't really differentiate from the other 2. So therefore, I think while we have achieved a continuous definition following Hillier logic, it appears that this kind of calculation approach may lack practical significance of what he tried to achieve in his study. Then the study tests the logic also he used for the D structure, which is the sum of all directions, regardless whether the directions lead back or diverge to the route that is not the shortest. And quite interestingly, the trend is pretty much the same as the first one we observed, despite the values actually are the twice of the first logic. So the A structure value increases with the no count, and the values for the D structure continuous have a value of 4. So in a way, you can see that both methods evaluated based on Hillier's example do not fully capture what he wanted in the theoretical base. And the evaluated values cannot really illustrate the potential for alternative route choices during the traversal, which is the very concept we think Hillier proposed for this new measure. So in other words, the methods Hillier apply in the calculation of mean local choice do not effectively align with the theoretical significance of the measure. If we put two trends together, it's pretty much the same. So building on this, we propose an alternative approach that understands what actually mean local choice should be and how it can reflect the theoretical significance. So instead of calculating the step-by-step alternatives, it considers all possible shortest paths for each spatial node within the configuration to traverse through all others. So here is an example. So if we then use the 7-node D structure. So for the node A, it has 12 alternative paths that allows it to traverse through all others with no revisit. And for the node B on the edge, it has 18 options to traverse through all other nodes. So this actually reflects the richness of the shortest path. So traversability measures the length of the shortest path. And mean local choice associated with traversability actually quantifies the richness of how many routes you will have to traverse via this shortest path. And if we use this logic to evaluate the values for the 4 structure types, we have the resulting trends like that. So the good thing is that we can now actually look at the trend of D structure in red. That is the very thing that makes this measure meaningful and also different from Hillier's approaches. So because it shows a clear difference in the D structure when compared to B and C structures. So as the node count increases, the mean local choice value for the D structure also rises. So this indicates that with a larger node count in the D structure, this is a D structure, there's a creation of more interconnected subcycles. So thereby, it can enhance the local choices you can select during your traversal. And also, if you look at the blue line for A structure, this is another thing because the nature of the factorial basis to calculating the A structure is surprisingly, I mean, it's very high compared to others. But the very thing we want to say that we, from this measure, D structure differences from B and C, and it's then possible to actually compare the real world configuration results, see how it may approach to B or to C or to D via these equations. And yeah, here's the summary of the formulas developed and examined in this study for calculating the 3 measures. So as I said, the formulas actually provide a research basis for comparing the calculated structural properties of the real-world layouts with those of the A, B, C, and D structures with the equivalent node counts. So such comparisons then make it possible to evaluate the significance of your real-world configurations by examining the extent to which they might approximate to a certain type of the theoretical structure type. And also, as mentioned before, there was no existing algorithm to calculate the 2 Hamiltonian city-related measures. So in addressing these, I have developed a Python-based program. This is to calculate both the length and number of the shortest paths for each node in the given spatial configuration to traverse through all others by the shortest path. And so it then possible to actually calculate the traversability and mean local choice values of the real-world configurations that are not simply a theoretical A, B, C, or D structure type, right? And as a recap, I showed this figure before. Hillier proposed that A and B structure correspond to long model, and C structure and D structure refers to the short model. But I have also questions from my class in UCL, the MSc. Like they ask, like, why Hillier use these terms like A and D structure creates short or long model activity, and B structure distance, and C structure access the short model activity. I mean, Hillier didn't really explain what he meant by creating, distancing, or accessing. And in answering that, I mean, using the algorithm and also the equation evaluations, the study conducted some experiments actually to further test how the three structural properties would in a way change when modifying the 7-node D structure graph as an example. So this first attempt is to progressively disconnect the central D space of the 7-node configuration from its surrounding edge nodes. So you can see as the central nodes become increasingly isolated from the edge nodes, the edge node change from D spaces to C spaces, of course, because it's now in a single circulation. And the graph eventually turns into a single circulation with the central node turning into a dead-end A space. And then if we use this kind of methodological framework, we can then compare and investigate how the values of total depth, traversability, and mean local choice change along this process of disconnecting the central D space. So the idea is that we compare the actual value of the graph after the change with the theoretical four type of structures, right? So if you remember, the D structure has the highest total depths, lowest total depths, meaning it's highly integrated, and it has the high traversability and the high mean local choice. So this is on the one side, and then B structure is on the other side. So if we put B structure on the one side and D structure on the other side, we can see how the actual values in between of these different structure types may approach a certain type of the theoretical structure with the equivalent node count. So yeah, so with this process of disconnecting the central D space, we see that firstly the total depth value show a consistent increase, meaning that the configuration is gradually segregated as the central space being disconnected. So in response, the general graph in a way becomes more closely aligned with that of a theoretical C structure if you see at the end, away from the D structure. And the traversability, on the other hand, remains unaffected by the disconnection process until the last step, which makes the whole graph a single circulation with one dead-end A space. So meaning that in the first 4 steps of the disconnecting, the graph remains a traversability of 1, meaning that all space require no revisit to visit all others in a continuous traverse. However, the mean local choice, if you see the right figure, also shows a gradual drop from actually 17 to 2.5. So meaning that even the traversability remains the same when disconnecting the central D space, the richness of options for the efficient traverse is actually reduced. So these are the two very individual measures, as you can see. So in other words, if you imagine both D structure and C structure are fully traversable, but in the D structure, you have many options. I can freely select whatever routes I want and without necessary revisit. But in the single circulation as the C structure, I only have 2 options when I start my journey, whether go left or go right, and then I have no options. So although they are all fully traversable, the richness of options differ. And the second attempt is to actually add the A and B spaces into this 7-node graph. So I have done some different attempts like adding 1 A space or 2 A space at 1 D space, or add 2 A space separately in different nodes, or add the D spaces in a different logic, right? So again, looking at the changes of values, so the first thing I noticed that addition of A and B spaces have a clear impact on the total depth, and it's particularly noticeable that adding the B space, meaning that extending the dead ends, right, has a very profound effect on increasing the total depth than adding the A space. So in other words, if we extend the existing dead end, will result in the most significant depth gain. And on the other hand, the addition of the A space, which are the dead ends, I'm sorry, the addition of the B spaces, which are the way to the dead ends, does not significantly impact the traversability value. The traversability value shows clear drop only when A space, the dead ends, is added. So it means that only when a new dead end is opened that the traversal system of the graph is more likely to be affected, instead of simply extending an existing dead end. So similarly, if you want to extend the dead end path by adding B space, does not clearly impact the changes in the mean local choice as well. Okay, so and the final attempt here for the experiment is to add C spaces. So in other words, is enlarging the circulations. And looking at the changes in the values, the total depth similar to the disconnecting central D space, the total depth also shows a consistent increase with more C space got added. And on the other hand, the traversability remains at 1, meaning that the enlargement of the circulations does not actually create unnecessary revisits for the traversal. And the mean choice, although it has a slight drop, but still remains quite high. Like even with 3 A-C spaces added, it has the value of 13, meaning that on average for each node, you have 13 alternatives to choose the shortest path for the traversal. So in other words, we can see that the addition of C spaces only makes the graph more segregated, but does not affect the organization of the global circulation patterns that is organized by the D spaces. So if we want to sum up, the very first observation is that the traversability proposed by Hillier as a very new kind of measure concept stands out as it is a very critical indicator to differentiate between the short and long model activities that are influenced by the spatial structure. So if you look at the comparisons, A and B structure has low traversability and C and D structure has high traversability. And it's also I think it's very easy to understand because imagine if you have a configuration with low traversability, it requires the frequent returns to the previously accessed spaces. This aligns with the concept of long model activity because it suggests a spatial layout that restricts the navigational freedom, right? Because it enforces you to have a movement pattern that characterized by the repeated passes through certain areas. So, and on the other hand, a configuration with the high traversability allows for uninterrupted navigation across the entire layout. So at least it enables the visitors to traverse the space in the single pass without the need for the backtracking. So it's indicate of at least a precondition, I think, for the short model activity where a more explorative movement patterns is facilitated. And back to the question, why Hillier said that B and C structure are not associated with the creation of short and long model activities, but rather distance or access these models. So if we look from the experiment, the addition of B spaces effectively extending the dead end paths have a minor influence on the traversability, right? But primarily contributes to an increase in the total depth. And in contrast, the addition of A spaces to a graph results in a significant drop in the traversability, leading to a less efficient system for the traverse with more unavoidable returns to the previously accessed spaces. So in a way, we can see opening the new dead ends, meaning that you are giving more restrictions to the global circulation, to the global movement. So it creates this kind of the notion of long mode activities, whereas the B structure syntax, in a way, only extend the existing dead ends. So it distance the or further enhance the long mode activity that created by the notion of A structure, but not solely generated by itself. And on the other hand, the theoretical C structure, as I said, is highly traversable, but we can see that free navigation can be limited and restricted because only 2 alternatives are available for such traversal. And many spaces are at a significant depth from the beginning point, like because it's a very long circulation path. So beyond the precondition of a traversable graph, a high global integration is also necessary for the ease of movement for one location to another, while a richness of alternatives, which is indicated by the main local choice, for the efficient traversal is also essential if we want to talk about the idea of the short model activity. And also from an experiment, as more D spaces were converted to C space, both the integration and main local choice consistently decreased. So it reduced the potential for free exploration. And on the other hand, the C space from the which form the basic components, right? Because D space is the organizer of the circulations. But if you want to have circulations, you need to have the C spaces, right? Forming the circulations. So C space is in a way the basic components, like the subcycles that are organized by the D spaces. So in other words, simply adding C spaces by extending the circulations have no impact on the traversability or route choice, but only making the graph more segregated and distanced. And from this perspective, I was trying to say that the fourth type of the structures, actually four type of the syntax one used to create the spatial configuration. And I believe it's the only four. And I always welcome, questions whether they are the fifth way of creating configuration rather than these four, because the A structure represent the creation of the new dead ends, right? It restrict the movement and exploration, and these configurations often lead to long model activities because the length of the restrictions are long, and due to the necessary of retracing steps. B structure, on the other hand, extends the existing dead end to the greater depths, so it further amplifying the limitations on navigation and promoting the long model activities. Whereas the C structure expands the single circulation routes, so it offers more continuous pathways but limited alternatives. So while the traversability of C structure is high, the depth and lack of choice, the mean local choice, can still constrain the free exploration. And lastly, D structure, it organizes and diversifies the circulations on a global scale. It facilitates a rich array of navigational choice and promotes the short modal activities through the enhanced integration and freedom of movements. So I think what can be understood from this concept or conclusion is that we can treat the four spatial, we call ourselves the space syntax, and from my own perspective, A, B, C, and D structure are the syntax we use. And it can lead to two kind of different alternatives to apply this framework. The one is that we can now interpret what kind of the consequences we may have when we design or alter the spatial configuration, right? We can say, okay, well, I'm using the logic of A or B or C or D to alter or design this kind of new layout or existing layout. This is one path. Now we know, because now we know the consequence from these experiments, like how the addition of C space or A space may lead to certain consequences and functional effects. The other way is the other way around. Like if we have an existing layout and we want to understand what it means regarding the functional effects, we now have a, in a way, reproducible and comparable approach. Like we calculate the real values of this layout and we compare the extent to which it approach to a theoretical layout, a theoretical structure. And because we know what theoretical structure now means regarding the social functioning and the so it is then confident or evidence-based in a way to discuss the real-world configurations in this sense. Yeah. And I think that's it. Thank you very much, and I'm happy to answer any questions.